right, subscribers, welcome back to another episode of Science with Surbeck. Today we check out sections 21.1 and 21.2, which gives us a little introduction to our business on nuclear chemistry. Now, we really just skimmed the surface, and remember, our focus in this particular unit is on the atomic structure, and you'll see why here momentarily this relates to our atomic structure. So before we get into the details of these notes, there are a few objectives that I want you to be able to accomplish by the end of these notes. Number one is to write the nuclear symbols for protons, neutrons, electrons, alpha particles, and positrons. Objective 2 is to complete and balance nuclear equations having been given all but one of the particles involved. Objective 3 is to write the shorthand notation for a nuclear reaction, or given the shorthand notation, write the nuclear reaction. Objective 4, and the final objective, is to determine the effect of different types of decay on the proton to neutron ratio and predict the type of decay that a nucleus will undergo based on its composition relative to the belt of stability. All right, so again, it sounds complicated here, but we get to this business here in notes. So around the same time that they're doing all this work on the atomic structure of elements and atoms, they are also identifying this radioactivity. Now, we have a really generic definition here, and just as a reminder, these yellow highlighted words that are written in red are the ones that you need to fill in your notes. But what they notice is that they have this spontaneous radiation. So essentially, we're going to really dumb it down here. Energy is given off by atoms. Okay, so they notice this energy being given off. Now, Marie and Pierre Curie, they are fundamental into doing this nuclear research. It actually had them get sick, but nonetheless, that was the start of it. So as we get into this, we need to be concerned about three main nuclear parts, or three main nuclear pieces that we have to be aware of. So we have this radioactivity, which is this radiation, spontaneous radiation. So again, think radiation as, hey, atoms are given off energy in some way, shape, or form. So our three main types of radiation are alpha, beta, and gamma radiation. Now, there are additional types of radiation, and we'll talk about a few as we get more into these details of these notes. But our alpha, beta, and gamma radiation, they are distinguished from one another by both their charge and as their mass. Okay, so charge and mass, which ultimately charge and mass are going to affect the nucleus. You can also see that these symbols for each of these quantities are written into parentheses. So alpha has the Greek symbol for alpha, beta, same thing, and then gamma, kind of looks like an upside down Y, is that symbol there. Notice how these are going to vary in terms of their charge, energy, and amount of mass. And that's important to keep in the back of your mind as we go through this process. All right, let's keep moving on here. Again, just getting underway with some definitions, some things to be thinking about with nuclear radiation. So nuclear reactions, again, sounds complex, but really all that happens here is we have changes in the atomic nuclei. And so this is why we throw this business in when we talk about the atomic structure. So when we have radiation, or when we have nuclear chemistry, we're really just dealing with changes in that nuclei. So we're either going to affect the number of protons, affect the mass by adding neutrons or taking away neutrons, and that's what we're going to be focused on. Now, radioactive substances. It's actually kind of a generic term when we look at it in terms of a chemistry standpoint, but something that is radioactive is just going to have the nuclei spontaneously emit energy. And almost all isotopes of any element are going to emit some energy. Some take longer than others to emit this energy, but almost all are going to have that spontaneous emission of energy. It's just determined, or each and every element has a determined half-life about when it's going to emit that energy. Okay, so let's get into the nucleus specifically and really get down to business in terms of what we have here. So, again, the reason that we throw nuclear chemistry into this particular section is because it deals with that atomic structure, specifically with that nucleus. So, in the nucleus, we have the proton and the neutron. Now, again, we've gone over this. The atomic number of each and every element is unique to the number of protons it contains. And the mass number is the number of protons plus the number of neutrons. Now remember, that mass number is going to vary depending on what isotope we have and what isotope we are dealing with. But again, we as we go through these notes are going to identify the nucleus as the nucleons. And basically what's that saying is, hey, what is happening to the parts and pieces of the nucleus as we go through a nuclear reaction? Again, all I want you to know is, hey, you may see this nucleon terms, just know we're talking about the nucleus. That's just a term they like to throw out there so that we can identify this. Okay, so we said that our mass number can vary, and that is because we have isotopes. So remember, just as a reminder from the last section, elements that have the same number of protons but different number of neutrons are going to be considered isotopes. So we're still dealing with the same element. The only difference is how many neutrons they have, which ultimately affects their number of mass number. So we have our example here of uranium-234. And just as a reminder, we can write it two different ways. Typically in nuclear chemistry, we are going to write it in this symbol notation. And that's because we identify the symbol, we identify both the atomic mass and the number of protons. Okay, so again, all of this should be review with the exception of, hey, nuclear radiation is simply just the emission of energy from that nucleus, okay? The other things should be relative review. As we get going here, we're going to introduce more and more terms, so we'll quickly go through some additional items here. So we get to another term here. Again, you may see this thrown out here, so I wanted you to be familiar. We have these nuclides. And so nuclides are just defined as a nucleus containing a specific number of protons and neutrons. Essentially, if you think about this, this is really describing an isotope. Okay, so one nuclide is different from another nuclide because it has a, again, specified number of protons and neutrons. Now, we could get a little bit more specific and we could have radionuclide, and this is saying, hey, these nucleus are radioactive. Now, that radioactivity is going to be determined most of the time through that belt of stability, which I mentioned in our objectives and we'll get to here towards the end of our notes. Okay? So, take a breath. I threw a lot of information at you. Again, this is just good to reference. The two things that you need to keep in mind here is this. Nuclear radiation is just the emission of energy from the nucleus of an atom. And then we have to deal, or nuclear chemistry stems from those isotopes. The reason that we have one isotope more radioactive than another is going to have to do with that number of protons to neutrons, which we'll talk about here in a second. But again, up to this point, all this is just terminology. So it's just throwing you some new terms. Again, nuclear chemistry likes to do that, but think simple here. How can my nucleus change in my atom? Okay, so let's get to actually nuclear equations. So again, this whole thing is centered around the nucleus. When I say nuclear equations, we are talking about the nucleus for our concept right here. We could get a little bit more in depth and in detail, but we're going to stay relatively simple here. So we have this here that says most nuclei are stable, which means that, hey, if we hold it in our hand, that nucleus is not going to decay on us over a certain time. But we've mentioned this before, that we have these radionuclides, and these are unstable nucleus where they're going to emit particles or they're going to emit electromagnetic radiation. Now, we haven't really talked about electromagnetic radiation, but just think about this. It's going to emit energy or particles. If you want to think about this, it's going to emit pieces from the nucleus. So we're either emitting energy or pieces from the nucleus, which sometimes pieces of the nucleus will also emit that energy. So we get to uranium-238. You may have heard of uranium being used as a fuel rod in something like a nuclear power plant or a nuclear submarine. And the reason for that is that it is going to emit what we call an alpha particle. Now, an alpha particle, we have shown, or we have just introduced that to you a few moments ago. And so specifically, an alpha particle is essentially a helium-4 particles. Now, one thing that it doesn't have is it doesn't have the electrons of the helium-4 particles. So essentially what we're dealing with here is we are dealing with a helium-4 nucleus. And again, we will see here in a second why uranium-238 goes through an alpha decay. But an alpha decay is going to help get this particular radionuclide as stable as possible, as quick as possible. And again, that will be helpful when we just briefly explain the belt of stability. All right, again, moving on here. We don't want to spend too much time. But we have radioactive decay, and it says this happens when the nucleus decomposes. So it's going to emit those particles or emit that electromagnetic radiation or energy. Okay? We have equations to represent that nuclear process. Now, you may be thinking, if you've never seen a nuclear equation before, you may be thinking, whoa, hold on, that sounds complicated. It's really not. All we're doing is we're tracking what leaves the nucleus and what atom is now present at the end of that decay. And it's very simple mathematics, and it's just utilizing, again, protons and neutrons. And now what do we have in the nucleus? And ultimately, what do we have as the element that we're working with? So we get to this, writing nuclear equations. Again, sounds complicated, but it's really just basic mathematics, and it's tracking what happens in that nucleus of that particular item. So very, very important here. It says the total number of nucleons is conserved. Okay? Protons, and neutrons equal on both sides. So we have a very simple equation, which we'll do here in a matter of moments. But what we have here, we have to keep track of both the mass number and the atomic number in each of these pieces. So this right here is uranium-238 going under our alpha decay, which this equation here uses a helium. You may see this. I like to actually put the alpha particle to represent that we have uranium-238 because, again, that makes us non-confused about dealing with electrons. Nuclear chemistry, we're not as concerned about electrons, but sometimes you'll see it written as this. Again, total number of nucleons is equal before and after reactions. So if you add up all the protons, they equal each other on the left and right hand side. And then if you add up all of the mass numbers, they are also equivalent. Okay, so let's go in and actually have some steps to write our nuclear equation. Okay, so our steps here. Number one, most important, write out what you have in terms of the isotope and do it in symbol notation to not only include the atomic number, but include the atomic mass. And this is important because, again, we need to track both the total mass and we need to track the total number of protons. Okay, so usually the decay is given. Sometimes you'll have to use the belt of stability to predict that. Then what you're going to do is you're going to write, if it says decay, that decay is going to be shown on the right hand side, and then you're just going to do some simple mathematics to get to your atomic number and number of protons for that next new element. Okay, so the best way to go through this is just through an example. All right, so our example here says what is the product that is formed when radium-226 undergoes alpha decay. Okay, so couple of things here. I'm just going to grab a periodic table, and the first thing is I'm going to find radium. Well, radium is written right here, and I want to write the symbol down, so that is Ra. So I start out with the symbol Ra, and then I'm going to put the mass number 226, and then down below I'm going to put the number of protons, or the atomic number, which if you look very closely, radium has an atomic number of 88. So we have 88 as our atomic number, and then it undergoes that decay. So the moment you see decay, that is essentially like that yield sign in our typical chemical equations. Now, what happens here is this. The first thing that I like to do is identify what type of decay we have. And so if you remember from the second page of notes here, an alpha is going to look like this. Okay, so your alpha is going to look like that symbol, and I haven't shown you the specific look-like of what an alpha symbol consists of, but it's going to have a mass of 4 and a 2 as the number of protons. Now what we need to ask ourselves is 4 plus what equals 226? So 4 plus what equals 226? Well, the answer to that is 222. Then we have to ask ourselves, okay, 2 plus what equals 88? Again, 2 plus what equals 88? Well, the answer to that is 86. So now, 86 is very, very important. And the reason for that is that 86 is not only the number of protons, but is the atomic number of that new element that is formed in the nuclear reaction. So what we do is we write down that symbol for that particular element. So we have Rn, radon, as our new element. And that's how we would write a chemical nuclear equation. So again, mass is conserved, number of protons is equal on the left and right hand side. We just have to remember, wherever that decay occurs, we have to add those together. Now, again, I didn't show you the symbols. I should have done that first, but we have them here on this particular page. All right, so again, we've gone over alpha and beta, but now we specifically have our examples here for alpha and beta. What we do over the next few pages is we throw a little bit more at you with this particular circumstance here. So what I want to direct your attention to, yes, keep writing these particular notes down, but this chart is very, very helpful. It shows you the symbols, and it shows you also the mass and the number of protons involved in each of these decays or emissions from this nuclear happening. Okay, so alpha, again, we've seen alpha. I like to write it as the alpha symbol because I don't like to confuse it with a helium atom, because sometimes you have that idea that we have to deal with electrons. Not the case with our nuclear reaction. Beta. Beta is essentially an electron, okay? So it is shown as a loss of an electron, which means it actually increases, if it's a beta emission, it actually increases the number of protons. However, because it has a 0 up top here, there is no mass. And so we have our example here. Iodine, atomic number 53, goes through beta emission. It actually increases that number of protons. And there is a very good reason about this. If we think about iodine and xenon, think to your back of your mind here, xenon is a noble gas. Okay? Noble gases are really, really stable. And so if we can lose an electron out of our nucleus, we can become stable. And so that's what this particular process happens here. Now, I want to talk about briefly here. It says it loses an electron from a nucleus. And you may be thinking, hey, we just talked about the atomic structure on the last section, and you told me that protons and neutrons are on the nucleus of the atom, and electrons are on the outside. And now you're saying, hey, the electron is lost from the nucleus? What exactly is going on here? And so what I want to do is I want to clarify this. I'm going to be very simple and straightforward here, and that is this. It is essentially losing a particle equal to that of an electron. It's not losing an electron out of the nucleus. So let me write that down. Okay, so again, we are dealing in nuclear chemistry with the dealing of loss of energy or gain of energy. So yes, we say, quote unquote, we lose an electron. But that's just easy math for us when we go to do the nuclear equation. So again, no, we're not losing an electron out of the nucleus. We're losing a particle or a piece of energy that is essentially equivalent to that of an electron. Okay, so there are 3 more types of radiation that I want to introduce. We've talked about gamma before, but again, the specific gamma radiation here, it just says, hey, we lose this high energy photon. So it's essentially saying, hey, we lose this pack of energy from the nucleus. Now, because this does not affect the number of protons or the mass numbers in an equation, I will tell you, hey, this has alpha emission along with gamma emission. So just like this problem says here, radium-226 undergoes alpha and gamma decay. So I'm going to indicate here that it has gamma decay. Because if I didn't tell you that, I would not be able to, or you would not be able to identify that particular particle. All right, so positron. This is going to be defined as a particle with the same mass as an electron, but the opposite sign. Again, I'm not going to write this down. You're not losing an electron out of the nucleus. You're losing a piece of energy that has the same mass of electron, but instead it is positive. Okay? So again, it's going to be based on stability for why this happens. Again, I just want to introduce these common types of radiation. All right, so last type of radiation here is going to be electron capture. Okay, so electron capture is when, quote unquote, the nucleus captures an electron from an electron cloud surrounding the nucleus. Okay, so again, think transfer of energy. What we're concerned in nuclear chemistry is how is that affecting our nucleus, and ultimately here in our example of rubidium going through this particular electron capture is we have the effect on our nucleus. Now here is the ultimate charge and mass effects for alpha, beta, and gamma decay. I'm not as concerned about this because I'm concerned about you writing simple equations involving these simple nuclear equations. So what I would do, I'm going to throw up the last page, is I would keep this chart handy as we go through these particular problems and identify some of those things. That will be helpful as we go forward here. Okay, so let's actually go through some examples here, and then we'll move on to why do some of those isotopes, why are they more radioactive than others? All right, so we have mercury-201 undergoing electron capture, okay? So we have to, again, identify the symbol for mercury. So mercury-201, we find mercury, and check it out. It has a symbol Hg and an atomic number of 80. So what we do here is this. Hg, 201 is the atomic mass, 80 is the number of protons. Now it says it undergoes electron capture. If you look on the previous page of notes, electron capture, we have to be careful here. Electron capture is written on that left-hand side or the reactant side if we're familiar with our chemical equations. Now we can simply add these numbers. So 201 plus 0 is 201, And 80 plus a negative 1 is 79. So that 79 is our number of protons, or our atomic number. So we check this out on the periodic table. 79 is equivalent to gold, or Au. Now, some of you may be wondering, okay, well, isn't electron capture the same thing as positron, where we reduce the number of protons and we don't add any atomic mass? Well, mathematically, yes, but think about this. The radiation for something that goes into electron capture, this is going into the nucleus, whereas positron emission is being emitted out of the nucleus. So it's depending on where that energy is flowing. Again, this is flowing into the nucleus, whereas positron emission would be flowing out of the particular nucleus. Okay, so it's the flow of energy, and that's what I've said all along. That's the really important thing that we have here. Now, this equation is a little bit different. It says thorium-231 decays to protactinium-231. Okay, so again, first thing that we need to do is identify our element we're working with. So we have thorium has an atomic number of 90. So we write down thorium as TH, and we write down 231 and 90. And it says it decays to protactinium-231. Well, protactinium has a symbol of Pa and an atomic number of 91. So we have Pa and 231 and 91. Okay, so now we need to think to ourselves, all right, well, what would not change the mass of the substance we're dealing with, but it would change the particular number of protons? Well, think about this. Think about this here. We could have a couple of things. Number one, we could have electron capture, but more than likely, we're going to have a beta particle, okay? So we're going to have the beta particle, which, again, has no mass, but has a -1 down there where we usually show the number of protons. Again, electron capture could work for this, but most likely, we are going to have our beta decay. Okay, so we will get more and more in depth as to why that happens as we introduce our last bit of information here for these notes. The other reason too that we use beta decay in this case is from this chart. Notice here where it says beta emission here, the atomic number is going to change by +1, whereas the mass is unchanged. Okay, so this kind of helps determine, it's our guide path for why we do what we do. So it's sometimes handy to have in mind. What I need you to focus on is, hey, if I tell you what the substance decays to, give me a source of decay that is possible. And then if I tell you, hey, what emission does it go under, you need to be able to predict that product, that new nucleus that forms. All right, so let's get down to business here as to why we have nuclear radiation in the first place. Why do we have those radionuclei? Okay, so we start out here with this neutron to proton ratio. That is the granddaddy of them all here, as to why we have nuclear radiation. And so what happens here is that proton is going to have a high mass and high charge. Okay, so remember, Proton's one of the two pieces that make up the majority of the mass. The majority of the mass in a particular nucleus. It also has a positive charge, and I'm going to put that in parentheses. And what happens here, we can think like magnets. As we start to get to the center of the nucleus, it becomes very, 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 very dense. And so we have this dense part with positive charges. Well, think like magnets. What happens when you bring those magnets closer and closer and closer and closer together? Well, they start to repel. Remember, likes repel. What we have this involved, or what we also have in the nucleus, is the neutrons. So those neutrons are kind of the buffer. And so now what I want you to think about here is that as we increase our atomic number, we're increasing the number of protons. And so if these neutrons are kind of the buffer to allow the positive charge to be very, very closely packed and densely packed, the more protons we put in a particular nucleus, the more neutrons we're going to need to act as that buffer. So we get to this point where we have this nuclear stability. Again, as we add protons, the repulsion is going to get larger and larger. You need that buffer of those neutrons to allow more protons to be in that nucleus. That is going to allow stability. However, you're going to reach a point where, hey, too much is in the nucleus, and we got to get rid of some stuff. So what happens is that nuclear radiation or that nuclear decay. It says, hey, those number of protons, we've reached our limit. We have too much stuff in the nucleus. We have to get rid of it. Okay? So what scientists have said or found is that as much as you can, elements like to have this 1-to-1 neutron to proton ratio. And as you vary from this 1-to-1 neutron to proton ratio, you're going to begin to decay in certain ways. Okay? So if you are above that belt of stability, you're going to undergo that beta emission. Now, what that means, remember, beta emission can also be written, I like to write it with the big B there, and have that same symbol. What this does, very important here, you may want to star this as an understanding. I'm not going to have you memorize it, but what this does is it decreases the number of neutrons to the number of protons. So essentially, you are getting rid of that proton to neutron ratio. You're trying to get as close to that 1-to-1 ratio as possible. Okay? Again, this is going to be above the belt of stability. And we'll see that here in just a second. If we're below the belt of stability, we're going to undergo that electron capture. Okay? So we are going to have that electron capture. Okay? So here's the belt of stability. And again, I don't expect you to memorize this. I just want you to have an understanding why certain nuclear radiation happens compared to others. Okay? So the belt of stability is this yellow line here. The red line represents a 1-to-1 proton to neutron ratio. Okay? So your neutrons are on your y-axis, your protons are on your x-axis, and as you get above this belt of stability, you are going to have that beta emission. As you get below it, you're going to have that positron positron emission or that electron capture. Okay, and again, we can have this as positron. This should be written as positron emission. Okay, and that's how this chart is written. Now, here's our big kicker. Nuclei with atomic numbers greater than 83 are going to undergo that alpha emission. Okay? The reason for this is that this is going to decrease the number of protons and neutrons the fastest. Again, the reason that we're undergoing radiation is we've reached our limit. We have too much stuff in that nucleus. And so at that point, we can't maintain that stability. We have to get rid of some stuff. That's why items with atomic numbers greater than 83 are going to undergo that alpha emission until they get to this point. Another reason for why as we increase our number of protons, the more likely we have a radionuclide. All right, so let's go over some examples to help recognize the belt of stability. And again, all I want you to do out of this is recognize, hey, there is a method to the madness of what type of radiation occurs and how we can actually predict that using that belt of stability. So we'll transition here. And what we're going to do, I'm actually going to pause the video. What I'm going to do here is I'm going to pause and I'm going to put the number of protons to neutrons in our examples. Okay, so the important thing here is we have our number of protons and our number of neutrons. Now, again, you could look at this chart more in depth, but what I'm going to say about these is either they're above or below the belt of stability. So carbon-14 here, based on this ratio here, is above the belt. And so in our chart here, it says anything above the belt undergoes the beta, which remember, big B, 0 minus 1, emission. Okay. Now, xenon has, again, a neutron to proton ratio that is seen here. And we have to be careful because that belt of stability does not follow that 1-to-1 ratio. It follows this, again, nice line. What happens here is this. Where our xenon 118 is a place where the neutron to proton ratio can actually increase. So this would be below the belt. And again, it's hard to see that, but the belt of stability is located a little bit above that 1-to-1 ratio. So it can either go through positron emission or electron capture. Now, plutonium-239. Plutonium-239 is above the belt. And check this out. Number of protons, 94. Remember what happens above 83 have to go through that alpha emission. Okay? Alpha emission. And remember, the alpha emission is essentially the nucleus of a helium atom. All right, so and then indium 120. Indium 120 is above the belt, and so above belt is going to undergo beta emission. So again, it's not an exact science as you can see here, but it is a way that you can predict what type of nuclear radiation that you would have on these particular substances. All right, so let's go through our last bit of business here, and this is our radioactive series. So radionuclide, if we've determined something has that radionuclide, we are going to want to determine, well, when does it get stable? So what a radioactive series is basically a series of radioactive decays or emissions that a nucleus undergoes until it becomes stable. So our example here is uranium-238. In this chart, it's probably a little bit better on your notes, but you can see that it undergoes each of these nuclear radiations or each of these nuclear emissions until it becomes stable at lead-206. So again, as we get these new nucleuses here, we undergo our nuclear radiation until we reach that lead-206. Now, how they predict nuclear stability, this is not as concrete, but what they have are these magic numbers. So typically what happens is if a nucleus has a certain number of protons or a certain number of neutrons as listed here, they are considered to be more stable than other nuclei that do not have these numbers. The reason for this is that it's going to correspond to filled closed shell nucleon configuration. Basically, they're filling all the gaps. They're not shoving more neutrons or protons into that nucleus than there should be. It is secured and it is kind of locked tight into that particular portion. Again, this isn't as concrete, but they have found, hey, if it has this many protons, this many neutrons, typically they are more stable than others. All right. So moving on here, our last bit of business just deals with that nuclear stability here. And for whatever reason here, nuclei with even numbers of protons and neutrons are more stable than with odd numbers. Again, they have to predict that it deals with that shell model of filling that nucleus with the correct number of protons and neutrons. Again, this is just one other way that they use to help predict how a nucleus is stable or unstable. All right, so the important things out of this particular section is this. Number one, be able to identify what is nuclear radiation, nuclear chemistry. Number two, be able to write nuclear reactions. So know those 5 types of nuclear decay or emission that we talked about and be able to write those particular nuclear equations. All other stuff here just supports why we have nuclear chemistry. Now we'll move on a little bit and we'll get into that half-life where we do make some of those predictions of how long a particular isotope is stable for. All right, so I hope you have enjoyed this particular episode, and if you haven't done so already, make sure you subscribe.